Okay, today we're going to talk about the history of the atom. Today we're going to talk about the history of the atom. We're also going to take a little field trip to talk about the history of the atom. And the thing you need to realize is we had to start somewhere in terms of what do we know about the atom. I know all of you know a little bit about the atom, but we're going to start from the very beginning. So we're going to go way, way, way back to our Greek philosophers about 200 BC. Now remember, Greek philosophers, we're talking, they're walking around in their togas, trying to come up with things and trying to get people to believe their ideas. Okay, they really had no scientific research to back up what they were trying to get people to believe. So we're going to first start with Democritus. He was a Greek philosopher. He was the very first person to propose that this idea of a very small, indestructible particle. Okay, so he was walking through the woods one day and said, hey, this tree, these leaves, the ground, these are all made up of matter. They are indestructible. And Democritus called this building block the atomos, which we all know as the atom, and that still sticks today. We call things the atom. We also had another Greek philosopher, Aristotle. He proposed that matter was continuous, meaning if I chop this table in half, I still have matter. If I chop it in half again, I can chop it in half again. There is no point where it's not matter anymore, okay? You can chop something forever and it's still matter, the atoms are there, okay? Whereas Democritus said there is a point where it ends. Okay, I can chop it in half a few more times, but there is a point where it is not considered matter anymore. So for a very, very, very long time, we just had those Greek philosophers and their ideas. Now we come to the 1800s. So we went well over 2,000 years just going with one of those Greek philosophers. John Dalton, was the very first person to propose an atomic model based on experiments. Okay, so he was in his house and he was doing experiments, and his theories are off of his scientific data. So a few things in terms of John Dalton's theories. One, he totally agreed with them that all matter consists of particles, and he still called these atoms. So even today, like I said, we still call them atoms. Now we get into the more nitty-gritty. He said atoms of one element can either be created or changed into other atoms of any other elements. What that means, if I start with a potassium atom, I cannot change into another element. Okay? It will always remain potassium. Atoms can either be created or destroyed. So those two kind of go together. Once it's there, it's there. I cannot create anymore. I cannot destroy that potassium atom. It will always be potassium. All atoms of the same element are the same in mass and any other properties, which means if I fill this room with all potassium atoms, every single potassium atom is exactly the same. Same mass, same properties, identical. Okay? Atoms of one element are different from other elements. So if I fill half this room with potassium, half this room with hydrogen, all the potassium atoms are the same, all the hydrogen atoms are the same. But if I compare the two, they are different. Different size, different mass, different properties. Which still sort of holds true today. Okay? Hydrogen atoms are different than potassium atoms. Then he also said, in compounds, these are when I can combine atoms of different elements, and when they combine to make these compounds, they combine in simple whole number ratios. Meaning, if I take a look at H2O, for every compound of H2O, I have 2 hydrogens and 1 oxygen. That is a simple whole number ratio. I cannot have half an atom. I can't have 3/4 of an atom. They need to be whole numbers. So that was John Dalton in about the 1800s. So we went about 100 years until Thomson came along. J.J. Thomson was the one that is known to discover the electron. What he used is the cathode ray tube. This is where rays appear on a screen, and here's an example of a cathode ray. Okay, you will notice that that ray that is going across the screen in that top picture, he said those were made of atoms. Now, the one thing that you do need to realize is they believe that the atom was neutrally charged. Okay, and so what he did is he took a magnet, and you can see on those bottom two pictures, there's a magnet on being close to that cathode ray tube. What he discovered is, which we all know with magnets, like charges repel, opposites attract. So when he stuck, in that first picture, when he stuck the positive end close to that cathode ray tube, it was attracted to it, which meant that that ray was composed up of negative things. And then when he flipped it over to the negative side of the magnet, you will notice that it's repelling it, which again proves that there is something negative in there. So he discovered the electron. He was also able to calculate the location of the electron and that charge of that atom. Okay? So he said that it was negatively charged and it was the electron. Now, he refers to this model as the plum pudding model. However, most of you guys don't even know what plum pudding is, so I like to use the analogy of a chocolate chip cookie. So if we think about a chocolate chip cookie, we have our dough, it's our atom, and then those chocolate chips are those electrons. Okay, those electrons are stuck randomly all throughout that atom, both inside, on the surface, all throughout. The dough part is kind of my positive sphere, because he still believed that there was a positive, the atom was neutrally charged. So if we have that electron in there, we have to have the positive in there to make it neutrally charged. So there's my J.J. Thomson. Now we go to Ernst Rutherford. A few years later, 1911, he did the gold foil experiment. Most of you guys probably are familiar with this. What he did is he stuck a piece of gold foil in the center and shot some alpha particles at that gold foil. What he thought was going to happen is he thought every single one of them was going to go through. That's not what happened. Okay? You will see from my picture that some went straight through, some were deflected slightly, some even shot back straight at the that source there. So what happened? Most of the particles did go through. About 98% of them did go through. Some deflected at different angles, and some bounced right back. So what does that tell us about the atom? Because most particles went through, that means the atom was mostly empty space. Makes sense? If I throw a ball through this room, it's going to keep going straight until it hits something. But if it doesn't hit anything, it's going to keep going. So most of the particles went through, empty space. Some deflected at different angles. Since they were deflected, it hit something. Okay? What he reasoned with that happening is it was hitting the nucleus, this dense core of the atom. Okay? And because some also bounced back, that dense core was also positively charged. So what did Rutherford discover? The atom was mostly empty space. He discovered the nucleus in that center, and most of the mass of that atom is in the nucleus, and that nucleus is positively charged. So now we have an idea of usually what most of you think what the atom looks like. It kind of looks like a peach according to Rutherford. Okay? We have the dense core, my peach pit, in the center. Most of the mass is in the center, and that fleshy part of the peach that we kind of all love and eat, obviously we don't eat the center, that fleshy part is where my electrons are floating around. Okay? So now at this point, 1911, we have my nucleus, we have my positively charged nucleus, and we have my electrons still floating around. Okay? So we know that inside that nucleus there are positive protons. We now move on to James Chadwick in 1932. He was the one that discovered the neutron. He said, okay, wait a second. I have this positively charged nucleus in the center. Why aren't those positively charged things bouncing off of each other? He knew there had to be something else in there that is kind of holding them together into this dense mass. He discovered the neutron. So now we know, 1932, we have my nucleus made up of protons and neutrons where most of the mass comes from. And then we have my electrons floating around. We now move on to the Bohr atom, Bohr model of the atom, 1913. If I were to ask you right now, draw a picture of the atom, this model is probably what you would draw for me. This is where he starts talking about electrons and energy levels. When I say energy levels, I'm almost talking like an onion. There are layers of electrons in that atom. So we got my nucleus, and then we have layers of electrons outside of there. These electrons can jump from level to level. Okay, so layer to layer of my onion. He said that these electrons travel in fixed paths, kind of like our planets. They do not veer from that path. Okay? The closer to the nucleus, the lower in energy, which kind of makes sense. There's not a lot of area that they have to distance, they have to travel. So it's very low in energy to go all the way around that nucleus, where if you're further away, you have a much larger circle to walk, so it takes more energy to do that. So closer to the nucleus, the lower the energy. So an analogy, I kind of used it already, is my planets. I have the sun, my nucleus, electrons and protons in there. And then my planets are circling around my nucleus. They do not veer from that path. It is a very fixed path. We now move on to the quantum mechanical model. Okay, this one gets a little tricky. Still dealing with electrons. However, he said these electrons do not travel in specific paths. Okay, there is no definite shape. It's one of those things where it may pop up here and then all of a sudden pop up there and then pop up there. It's very random as to where these electrons are traveling. He also said that these location of the electrons, it's all a probability. It's kind of like, though, at 5:30 at night, 90% chance that I am sitting down for dinner, because that's when we always sit for dinner. However, there's that 10% chance that dinner isn't ready, or we're doing something else, we're not at home that day. But that 90% chance is very big that I will be doing that at that particular moment. The same thing with electrons. Okay? The location of the electron is all a probability, which means I cannot say there is an electron in my hand at this particular moment. I cannot do that. I can say, though, there's a 90% chance that there is an electron right here. 90% chance is pretty good, but I cannot determine the exact location of an electron. And that's still true today. It is all a probability. So this one is kind of like a fan at high speeds, where if you turn on a fan at the highest speed, you can sort of see the blade, but not really, and you can just predict, okay, there's a 90% chance that the blade is right there at that particular moment. And today's modern view of the atom, it's very kind of all of them smashed into one. It's very like that Schrodinger one. The atom is mostly empty space. We have my nucleus that is protons and neutrons in the center. And then we have this electron cloud where my electrons are. Okay? We still have energy levels in those electrons, but those electrons do not travel in specific paths. And it's just more of like a region of where they're actually located. Okay? So that is the view of the atom that we know now. A few things you need to remember. Protons and neutrons are in the nucleus. Electrons are in the electron cloud. We cannot determine the exact location of the atom. Okay? And the other thing you need to remember is the atom is mostly empty space, because that space is my electron cloud, and there isn't very many electrons in that electron cloud, even though we're talking about something that is extremely, extremely small. Have fun, guys. The atom is oh so fun.